We humans have always been in search of patterns. They make us feel comfortable. They give us meaning. Nature and mathematics are no exceptions to that list when it comes to pattern seeking. In fact, they are at the forefront of it. One of these so-called patterns that has fascinated mathematicians and individuals for centuries is the golden ratio, also known by the Greek letter phi. It can be defined by taking a line and breaking it into two pieces. If the ratio of the lengths of these pieces is equal to the ratio of the original line and the now larger piece, the portions are said to satisfy the golden ratio, which is roughly equal to 1.618033 and so on. This is an irrational number. But what makes this ratio so irrational and so golden? To understand, let's simulate nature's one of the most elaborate mechanisms, a flower. Imagine you're a flower. Your job as a flower is to deal with your seeds. We are going to model and grow these seeds in the mathematical way by taking an arbitrary center represented here by this cross, and each seed will be represented by this small circle. One way to go is by putting the seeds randomly around the center, but that's not efficient. Another way we can approach is by putting one seed at the center, rotating by some amount, putting another seed, and so on. By this process, if you do a zero rotation, you end up having a straight line and a lot of wasted space. If you do half a rotation, it just forms two spokes. Similarly, if you do 1/10 of the rotation, you get 10 spokes. For 4/10 of the rotations, you get 5 spokes, and so on. These patterns are pretty, but not what flowers do. When we start playing with the values, making them less and less rational, you start to get these spirally shapes, and very quickly they stop looking like spokes. And this is already looking a better and prettier arrangement for a flower. How about we try some irrational numbers that we know, the pi or the square root of 2. It already looks great for pi, and even prettier and near perfect for 1 over root 2. But we have numbers which are even more irrational. For example, the golden ratio. If we put the golden ratio in the generator, the pattern that emerges looks best so far. This is what people claim happens in sunflowers and nature in general. The efficiency of this arrangement seems to perfectly balance between the least space used and the most seeds planted. But how is this justified? Let's see. If we take the number pi, whose value is 3.14159265 and so on, we can write it as 3 plus something. But let's write this in more detail and where it looks more like a fraction instead of a decimal. Since this bit is less than 1, it is 3 plus 1 over something. Calculating that gives 7 point something something. If we carry on this process, we end up having a fraction like this. This is called the continuous fraction of pi. But as you see here, just at the 4th place, the denominator below 1 is massive, which makes the fraction very, very small in value, which implies we can chop off the fraction here and approximate the value of pi with ample amount of accuracy. One thing you notice is that we ended up approximating the value of pi quite early on, which is why we can claim that pi is not very rational, and looking at the diagram, it still shows some remnants of spokes. So what would the most irrational number look like? It would be the one whose continuous fraction does not have any large number, which would look something like this. Well, just as a heads up, the continuous fraction for root 2 looks like this, which incidentally why root 2 looked near perfect in our diagrams. Because although they are not the smallest numbers, they are consistent and they stay small. So what is this number then? If you look closer, this piece of the fraction below 1 is same as the whole fraction, something like a fractal. Which means we can just write the equation as x is equal to 1 plus 1 over x and can be solved as a quadratic equation. After solving, what we end up having is the value of x as 1 plus root 5 over 2 or 1 minus root 5 over 2, which is equal to 1.6180339 and so on, or minus 0.6180339 and so on, which are the values of the golden ratio. This is why nature has chosen this number. Its irrationality and beauty is beyond admiration. The angle of rotation that we observed for 1 over 5 is 137.5 degrees, which is known as the golden angle in mathematics. But this number is not new for the universe. Quite surprisingly, 137.5 is the ideal angle of divergence observed in nature. In fold phyllotaxy, the angle between two subsequent leaves is roughly 137.5. Also, 137 is the highest possible atomic number which can fit into the modern periodic table if you go by Bohr's atomic model. This number is staggeringly close to the quantification of the fine structure constant, which is known to be the magic number that holds our universe together. Its value is about 0.00779927, which is surprisingly equal to 1 over 137.5. The coupling constant, which is the amplitude for a real electron to emit or absorb a real photon, if you take the inverse of its square, it turns out to be 137.035. In truth, the divine proportions owes its divinity not to some all-pervading transcendental property, but rather to the idea of beauty and perfection that we have imposed on it. In trying to find that perfection, we could nonetheless keep defining phi, but remember, it's irrational. Phi does not end, and neither does our search for beauty in this universe we live in.